Welcome back to This Week in Biochar. Every week we try to bring you the most exciting and impactful developments in the world of biochar. And this week, you, our listeners, have really outdone yourselves with your picks. We've got a great lineup today.
Yeah, two really cool things to dig into. First, a deep dive into the world of biochar and hydrochar. We'll be comparing their properties and looking at what makes them so similar and yet so different.
Sounds like a head-to-head matchup.
It is, kind of. And then we're going to shift gears and explore some cutting-edge research on how to really optimize biochar production, specifically from agricultural waste like sugarcane bagasse and corn cob.
I'm really excited about this one. Figuring out how to use these abundant resources effectively could be a game changer for biochar's future, right?
Couldn't agree more. Okay, so first up, let's tackle that biochar-hydrochar comparison. The study we're looking at is a bibliographic analysis, which basically means they've reviewed a ton of existing research papers on both materials to get a really comprehensive picture of the field.
And one of the first things that jumped out at me was this massive surge in research publications for both biochar and hydrochar, especially after 2010 and leading right up to the Paris Agreement in 2015. And that's got to be a sign that something big is happening here, right?
Yeah, no doubt. It's like the scientific community woke up and realized, hey, these biochars and hydrochars, they might just be key players in tackling this whole climate change thing. And, with the Paris Agreement setting those ambitious targets for reducing greenhouse gas emissions, the search for effective carbon sequestration solutions really kicked into high gear.
Makes sense. So the study also pointed out that there's often this kind of, I don't know, bit of confusion around the terms biochar and hydrochar. Sometimes they're used interchangeably. But for our deep dive, and this is something the study really emphasizes too, it's important to treat them as separate entities with their own distinct production methods and, well, personalities, almost.
Exactly. Like, you know how some people say all squares are rectangles, but not all rectangles are squares? It's kind of like that. Sometimes biochar is used as this umbrella term that encompasses hydrochar, but they're not exactly the same. And to understand their differences, we need to look at how they're made.
Right, let's get into those recipes. So biochar, that's all about pyrolysis, right?
hmm
Heating biomass in a low oxygen or a no oxygen environment at high temperatures.
hmm
Think like 400 to 700 degrees Celsius.
Yeah, you got it. It's like baking. But instead of cookies, we're creating this stable, carbon-rich material. And the study mentions that there are different ways to do this pyrolysis. You've got slow pyrolysis, where the heating's slower and the vapors stick around longer. And then you've got fast pyrolysis, which is more like a quick flash of heat.
So like slow roasting versus grilling, essentially.
I like that analogy. And speaking of definitions, it's important to remember what we actually mean when we say biochar. It has a specific meaning, right?
Oh, yeah, I remember reading about this. So it's not just about burning stuff for energy.
Right. The World Biochar Certificate and Carbon Standards International, they define biochar as this porous, carbonaceous material. It's specifically meant for locking away carbon or even replacing fossil fuels in industrial processes, not just for burning to create energy. It's about carbon sequestration and sustainable solutions, not just quick energy release.
Got it. So moving on to hydrochar. This is where water comes into play, right? This process, called hydrothermal carbonization, or HTC for short, involves heating biomass in water under high pressure.
Yep. Think of it like a pressure cooker for biomass. You're cooking it in water at a much lower temperature than pyrolysis, somewhere between 180 and 250 degrees Celsius. And that superheated water is what really drives the transformation. It dissolves certain organic compounds and helps create this carbon-rich solid we call hydrochar.
And the end product, hydrochar, still ends up being pretty high in carbon, right?
Absolutely. It can contain up to 60% carbon, so it's definitely a carbon-rich material. But here's a key difference in the production processes: the moisture content of the starting biomass. Pyrolysis needs pretty dry material, less than 30% moisture, which often means extra steps and costs to dry things out beforehand. But HTC, it can handle wet biomass and waste directly. No need to dry it first.
Ah, that's a big advantage for HEC,
Yeah.
especially if you're dealing with a lot of waste material. Less processing, potentially lower costs. I like that.
Yeah, it's a big plus. And the study actually points out that HTC kind of mimics the natural process of humification, which is how organic matter breaks down in soil over time. It's like we're speeding up that natural process in a controlled environment.
Fascinating. So we've got these two different processes, different temperature ranges, and even different moisture requirements. But what about the final products, the actual biochar and hydrochar materials themselves? The study talks about degradation, dehydration, all these chemical transformations happening in both processes. So are they really that different in the end?
That's the million-dollar question, right? Well, both pyrolysis and HTC involve breaking down the biomass, removing water, stripping away carbon dioxide, releasing methane, and forming new, larger molecules. But remember, it's like cooking. Even if you start with similar ingredients, the way you cook them drastically impacts the final dish.
So the high heat and lack of oxygen in pyrolysis versus the lower heat and pressure cooking with water in HTC, those lead to different characteristics in the final product.
Precisely. The specific temperature, the duration of the process, the presence or absence of water, all these factors influence the physical and chemical properties of the biochar and hydrochar. It's like fine-tuning a recipe to get the exact flavor and texture you want.
So how do scientists figure out these characteristics? The study mentions all these tests, proximate analysis, ultimate analysis, and this thing called a Van Crevelen diagram. Okay, I need a crash course here. What are these tests telling us in a practical sense?
Well, think of proximate analysis as getting the nutritional label for your biochar or hydrochar. It tells you the basic breakdown. How much moisture is in there, how much pure carbon, how much volatile stuff that can easily turn into gas, and how much ash is left behind. It's like the basic facts you need to know.
Okay, makes sense. And then ultimate analysis takes things a step further.
Exactly. It delves deeper, revealing the precise elemental makeup of the char. It tells you how much carbon, hydrogen, nitrogen, sulfur, and oxygen are present. And this information is crucial for predicting how stable the material will be, how it might react in different environments, and ultimately what applications it might be best suited for.
And the Van Crevelen diagram. That one sounds a bit more complex.
It's actually a really cool visualization tool. Imagine a graph where you plot the hydrogen to carbon ratio against the oxygen to carbon ratio for different materials. By plotting different types of biochar and hydrochar on this diagram, you can see how their composition compares to other carbon-rich materials like wood, peat, or even coal. It's like a mapping out their evolutionary path from fresh biomass to more stable forms of carbon.
So by looking at where a particular biochar or hydrochar falls on this diagram, you can get a sense of its stability and potential uses.
Precisely. And the study even provides a visual representation of this, showing how different biochars and hydrochars tend to cluster on the Van Crevelen diagram. It's a great way to get a big picture view of their characteristics.
The study also mentions that biochar tends to be more stable than hydrochar, both in terms of heat and chemical reactions. Is that because of the higher temperatures involved in pyrolysis?
You hit the nail on the head. That intense heat in pyrolysis forces the carbon atoms to rearrange into these tight ring-like structures, kind of like tiny sheets of graphite. And this structure, we call it aromaticity, makes biochar super resilient. It's less likely to break down or react with other stuff over time, which is a big deal if you're looking to lock away carbon for the long haul.
So more stable means better for carbon sequestration.
Exactly. If you want to store carbon in the soil for decades or even centuries, biochar's got a clear advantage over hydrochar because it's less likely to decompose and release that carbon back into the atmosphere.
Now, the study delves into a whole array of characterization techniques, and it's kind of mind-boggling how many ways there are to analyze these materials. We're talking about everything from adapting standard coal analysis methods to using high-tech spectroscopy. What are some of the key takeaways from all these techniques, and what do they actually tell us about the biochar and hydrochar?
Yeah, it's like a whole forensic toolkit for biochar and hydrochar. And one interesting thing is that because they're relatively new materials compared to, say, coal, which has been studied for centuries, there aren't always these readily available standardized methods for analyzing them.
So scientists are having to get creative.
Absolutely. For basic stuff like proximate analysis, they often adapt existing guidelines from organizations like ISO and ASTM, which are commonly used for coal and coke. But when they want to dig deeper and get a more precise understanding, they bring in the big guns, like these sophisticated spectroscopy instruments.
You can give me an example.
Sure. One technique they highlighted is thermogravimetric analysis, or TGA. Basically, you heat the material in a controlled way and precisely measure how much weight it loses at different temperatures. This tells you a lot about its thermal stability, and by analyzing the gases that are released during heating, you can even glean clues about its potential environmental impact. It's pretty neat.
So TGA is like a heat stress test for biochar.
Exactly. It shows how it holds up under pressure, so to speak.
Okay, I remember the study also talked about surface functional groups, those tiny chemical attachments on the surface of the biochar and hydrochar. Why are those so important?
Well, imagine the surface of a biochar particle, like a microscopic landscape, with all these tiny hills and valleys. And on those hills and valleys are these chemical groups, kind of like little flags sticking out. Those are the surface functional groups. And they're super important because they dictate how the biochar or hydrochar interacts with its surroundings.
So they're like the interface between the biochar and the rest of the world.
Exactly. And depending on what kind of functional groups are present, the biochar might be more attracted to water or repel it. It might prefer acidic or alkaline environments, or it might have a strong affinity for certain pollutants. Techniques like Boehm titration, FTIR spectroscopy, and XPS are used to identify and measure these groups, which is essential for figuring out the best use for a particular biochar or hydrochar.
Makes sense. pH and surface charge are also mentioned as important factors. The study even brings up this thing called the point of zero charge. Can you break that down for me?
Sure. So we all know pH, right? It's a measure of how acidic or alkaline something is, and it affects the chemical behavior of substances. The International Biochar Initiative, or IBI, they've actually developed a standard method for measuring pH in biochar. But surface charge is a little trickier to grasp.
I'm all ears.
Well, imagine the surface of a biochar or hydrochar particle as having these tiny positive and negative charges, kind of like magnets. Now, the point of zero charge, or PZC, is the specific pH at which the number of positive charges and negative charges on the surface perfectly balance out, so it's neutral overall.
So it's like finding the equilibrium point.
Exactly. And knowing the PZC is really important because it tells you whether the material will be more likely to attract and hold on to positively charged pollutants or negatively charged ones. It dictates its absorption preferences, so to speak.
Interesting. So pH and PZC, those are key factors to consider when choosing a biochar or hydrochar for a specific application, especially if you're trying to remove certain pollutants from water or soil. The study also touches on electrical conductivity. What's the significance of that for biochar and hydrochar?
Electrical conductivity basically tells you how easily electric current can flow through the material. It's related to the concentration of charged particles or ions within the biochar or hydrochar. And it can affect things like how readily plants can take up nutrients from the material, how well it can absorb other substances, and even its potential use in certain electrochemical applications.
So electrical conductivity is another piece of the puzzle when it comes to understanding how biochar and hydrochar behave and what they might be good for.
Precisely. And just like for pH, the IBI has a standardized method for measuring electrical conductivity in biochar, so we're starting to get a better handle on these properties.
Moving on to the physical structure, the study talks about techniques like SEM and BET analysis. These give us a glimpse into the microscopic world of biochar and hydrochar, right?
They do. These are the tools that let us see what's going on at the nanoscale, the very tiny details that we can't see with the naked eye.
So what kind of insights do we get from these techniques?
Well, XRD, or X-ray diffraction, tells you about the arrangement of atoms within the material. It reveals whether the char is crystalline, meaning the atoms are arranged in a very ordered pattern, or amorphous, meaning it's more random and less structured.
And SEM, scanning electron microscopy. That gives us those amazing images of the surface.
It does. It's like taking a high-powered microscope to the biochar and hydrochar, revealing all these intricate details like pores, cracks, and the overall surface texture. And often, SEM is combined with EDX, which analyzes the elemental composition at specific points. So you can see what elements are concentrated where.
Fascinating. And BET analysis, that one tells us about the surface area and porosity, right?
Exactly. BET stands for Brunauer-Emmett-Teller, and it's a technique for measuring the total surface area and pore volume of materials. It's based on the idea that nitrogen gas molecules can stick to the surface of the material, and by measuring how much nitrogen sticks, you can calculate the total surface area available.
And why is that important?
Well, the greater the surface area and the more porous the material, the more places there are for things to interact. For example, in soil, a high surface area means the biochar can hold on to more water and nutrients, making them available to plants. And for filtering water, more pores mean more places for pollutants to get trapped.
So BT analysis is crucial for understanding how well biochar and hydrochar can function in different applications.
Absolutely. It's one of the most fundamental measurements we can make to assess their potential.
Finally, the study talks about heavy metals. It makes sense that we'd want to know what's in these materials, especially if we're thinking about using them in environments where food is grown or where they might come into contact with drinking water.
Absolutely. We need to make sure we're not introducing harmful substances into sensitive ecosystems. And that's where techniques like ICPOES and ICPMS come in. These are super precise methods for measuring the concentration of different elements in a sample, including heavy metals like lead, cadmium, and arsenic.
So they're like detective work for heavy metals.
Exactly. They can tell you exactly how much of each element is present, even in trace amounts. And this information is crucial for assessing the safety and suitability of biochar and hydrochar for various applications.
And the study mentioned something interesting about the HTC process and heavy metals.
Oh, right. So it turns out that during HTC, some of the heavy metals present in the biomass can actually dissolve into the liquid byproduct, while others stay trapped in the solid hydrochar itself. It's a bit like a separation process.
So it's not just a matter of looking at the final hydrochar, but also understanding what might be in the liquid byproduct.
Exactly. And this has important implications for how we handle and dispose of that byproduct, especially if it contains significant levels of heavy metals. It's another reminder that we need to carefully consider the entire production process and its potential environmental impacts.
Shifting gears a bit, the study also did a kind of keyword analysis of all the research papers on biochar and hydrochar. What did that reveal about the main areas where these materials are being investigated for potential use?
Well, despite their differences in production and properties, the analysis showed that both biochar and hydrochar are being studied for very similar purposes: dealing with waste, cleaning up environmental contamination, and improving the health and productivity of agricultural soils.
So there's a lot of overlap in their potential applications.
Definitely. Both materials show promise in tackling some of the most pressing environmental challenges we face today.
The study even provides a handy table that directly compares the key property differences between biochar and hydrochar. It seems like biochar generally takes more energy to produce, but it tends to have higher electrical conductivity, greater ability to absorb other substances, and more internal pore space. Hydrochar, on the other hand, is often more acidic and has a higher affinity for water.
Yeah, that's a good summary. And these differences in properties really highlight the fact that each material has its own strengths and weaknesses, making them better suited for different applications.
Can you give some specific examples?
Sure, when it comes to improving soil, both biochar and hydrochar can enhance soil structure by increasing porosity, water retention, and aeration. But biochar, with its larger surface area and generally higher pH, is often better at holding onto nutrients, preventing them from leaching out and making them available to plants over time. Hydrochar, on the other hand, might be better at providing a quick boost of nutrients, especially in acidic soils where its lower pH can help neutralize the acidity.
So biochar is more of a slow-release fertilizer, while hydrochar provides more immediate effect.
That's a good way to put it. And when it comes to carbon sequestration, biochar's greater stability makes it a more reliable option for locking away carbon in the soil for the long term. While hydrochar can also contribute to carbon sequestration, it might not be as effective in the long run because it's more likely to break down over time.
And for cleaning up pollution.
Both materials can be effective at removing contaminants from water and soil, primarily through adsorption, which is the process of molecules sticking to a surface, but their different properties lead to different mechanisms of adsorption. Biochar, with its pore structure and surface chemistry, can trap contaminants both physically by trapping them within its pores and chemically through interactions with its surface functional groups.
So it's a two-pronged approach.
Exactly. Hydrochar, while it might have less pore space, primarily relies on chemical binding to remove contaminants. It's all about those surface functional groups grabbing onto the pollutants.
So the choice between biochar and hydrochar really depends on the specific application and the types of contaminants you're dealing with.
Absolutely. It's a matter of matching the right tool to the job.
Okay, let's move on to that second piece of research you mentioned. The study on optimizing biochar production from sugarcane bagasse and corn cob using vacuum pyrolysis. This one really caught my eye because it tackles the issue of agricultural waste head-on.
Yeah, this study is a great example of how we can turn a waste problem into a valuable resource. The study highlights the fact that globally we produce a staggering amount of agricultural residues every year, over 659 million tons. And figuring out what to do with all that waste is a huge challenge.
I remember reading about this. In some parts of the world, they just burn it, which obviously has a negative impact on air quality and contributes to greenhouse gas emissions.
Exactly. So, finding alternative ways to manage this waste is crucial, and this study explores one promising approach: converting it into high-quality biochar.
And they specifically focus on sugarcane bagasse and corn cob.
Yes, because these are two of the most abundant agricultural residues produced worldwide. Sugarcane bagasse is the fibrous residue left over after sugarcane stalks are crushed to extract their juice, and corn cob is, well, the central core of an ear of corn after the kernels have been removed. Both are readily available in large quantities, making them ideal candidates for biochar production.
Makes sense. And the study uses a special type of reactor called a vacuum pyrolyzer. What's so special about vacuum pyrolysis?
Well, in traditional pyrolysis, you heat the biomass in the presence of some air, which can lead to unwanted side reactions that can actually degrade the quality of the biochar.
How so?
Imagine you're building a house of cards and suddenly someone turns on a fan, the cards start flying around, and becomes much harder to build a stable structure. That's kind of what happens in traditional pyrolysis. The oxygen in the air can react with the volatile components of the biomass, creating all sorts of byproducts that can clog up the pores of the developing biochar, reducing its surface area and overall quality.
So vacuum pyrolysis is like building that house of cards in a calm, controlled environment.
Exactly. By removing the air and creating a vacuum, you prevent those unwanted side reactions, allowing the biochar to develop a more porous structure and retain more of its beneficial properties. It's like creating a more refined and controlled product.
So the researchers in this study took sugarcane bagasse and corn cob and processed them in a vacuum pyrolyzer at different temperatures, ranging from 500 to 700 degrees Celsius. And then they analyzed the resulting biochars using a whole battery of tests, right?
That's right. They looked at the basic composition with proximate and ultimate analysis, the physical structure and surface area with SEM and BET analysis, the mineral composition with XRD, and the thermal stability with TGA. It's a really comprehensive characterization of the biochars produced under different conditions.
And the goal was to see how the pyrolysis temperature affected the final properties of the biochar.
Exactly. They wanted to find the sweet spot, the temperature that would yield the highest quality biochar with the most desirable characteristics.
So what did they find?
Well, first of all, they found that as the temperature increased, the yield of biochar actually decreased. This makes sense because at higher temperatures, more of the biomass gets converted into gases, leaving less behind as solid biochar.
So it's a trade-off between quantity and quality.
Exactly, but here's the interesting part. Even though the overall quantity of biochar decreased at higher temperatures, the quality, in terms of its porosity and surface area, generally improved.
So less biochar, but better biochar.
Precisely. And they also noticed that the yield of biochar in vacuum pyrolysis was slightly lower than what's typically seen in traditional pyrolysis, which they attributed to the vacuum helping to remove the vapors more quickly, giving them less chance to condense back into the solid biochar.
Makes sense. Now, the proximate and ultimate analysis revealed some significant changes in the biochar compared to the raw sugarcane bagasse and corn cob. What were some of the key findings?
Well, they found that the amount of fixed carbon in the biochar increased dramatically as the pyrolysis temperature increased. Fixed carbon is essentially the pure carbon that's left behind after all the volatile components have been driven off, and it's a good indicator of how stable the biochar will be in the environment.
So more fixed carbon means more stable biochar.
Exactly. And the percentage of carbon in the biochar also increased significantly, reaching up to around 90% at the highest temperatures. This is a big deal because it means the biochar is becoming more and more like pure carbon, which is highly stable and resistant to decomposition.
That's impressive. What about the other components of the biochar?
As expected, the volatile content, which is basically the stuff that can easily turn into gas, decreased as the temperature increased. And as more of the organic matter was converted into gas, the percentage of ash, the inorganic mineral component, also increased.
And how did the energy content of the biochar compare to the original biomass?
They found that the higher heating value, or HHV, of the biochar was significantly greater than that of the raw sugarcane, bagasse, and corn cob, even approaching that of some types of coal. This is another indication that the biochar is becoming more energy dense and could potentially be used as a fuel source.
Interesting. Now, the BET analysis results are particularly intriguing. They found that the surface area and pore volume of the biochar increased as the pyrolysis temperature increased up to 600 degrees Celsius, but then they started to decrease at 700 degrees. What was the reason for that?
Well, the initial increase in surface area and porosity is likely due to the breakdown of the biomass structure and the release of volatile compounds during pyrolysis. As the biomass heats up, the volatile components escape as gases, leaving behind a network of pores and channels within the biochar.
So it's like creating a sponge-like structure.
Exactly. And the higher the temperature, the more volatile components are released, leading to a more porous structure. But at a certain point, the temperature gets so high that the mineral ash within the biomass starts to melt.
Ah, I see. And when that molten ash cools down, it solidifies and blocks some of those pores, reducing the overall surface area and porosity.
Precisely. It's like pouring concrete into a sponge. It fills in the spaces and makes it less porous.
This images really help to visualize these changes, showing the transformation from the smooth, relatively non-porous surfaces of the raw biomass to the intricate honeycomb structures of the biochar. It was fascinating to see how the surface morphology evolved with increasing pyrolysis temperature.
It really highlights the dramatic physical changes that occur during pyrolysis.
The XRD analysis also provided valuable insights into the mineral composition of the biochar. The study mentions that the distinct crystalline structure of cellulose found in the original biomass disappeared in the biochar, indicating the formation of a more amorphous, carbon-rich material.
That's right. Cellulose is a major component of plant cell walls, and it has a very ordered crystalline structure. But during pyrolysis, that structure breaks down and the carbon atoms rearrange into a more random, amorphous arrangement.
So the biochar is essentially becoming less ordered and more like a random network of carbon atoms.
Exactly, and this amorphous structure contributes to its stability and resistance to decomposition.
The XRD analysis also revealed the presence of various mineral components in the biochar, like silica, potassium carbonate, and calcite. What's the significance of these minerals?
Well, the presence of minerals like silica and calcite suggests that the biochar could have some alkaline properties, which could be beneficial for neutralizing acidic soils. And potassium carbonate is a valuable nutrient for plants, so its presence in the biochar could enhance soil fertility.
So the biochar is not just a source of stable carbon, but it can also contribute to soil fertility.
Absolutely. It's a multifaceted material with a lot of potential benefits.
Finally, the TGA analysis showed that the biochars produced from sugarcane bagasse and corn cob using vacuum pyrolysis exhibited high thermal stability. What does that mean in practical terms?
It means that the biochar is resistant to breaking down at high temperatures. The study found that there is very little weight loss below 400 degrees Celsius, indicating that the biochar can withstand significant heat without decomposing.
So it's a very durable material.
Yes, and this durability is one of the reasons why biochar is so promising for long-term carbon sequestration. Once it's incorporated into the soil, it's likely to persist for a long time, effectively locking away that carbon and preventing it from returning to the atmosphere.
And the study also mentions that the type of biomass used, sugarcane bagasse versus corn cob, had a more significant impact on the final surface area of the biochar than the specific temperature within the range they tested.
That's right. They found that the sugarcane bagasse biochar generally had a higher surface area than the corn cob biochar, regardless of the pyrolysis temperature. This highlights the importance of carefully selecting the right biomass feedstock for biochar production, as different feedstocks can lead to significantly different biochar properties.
The researchers also used a statistical method called response surface methodology, or RSM, to optimize the production conditions. What did they find?
Well, they found that the optimal conditions for maximizing surface area in the sugarcane bagasse biochar were a pyrolysis temperature of around 595 degrees Celsius. And this prediction from their model was very close to the actual experimental results they obtained at 600 degrees Celsius.
So their model was accurate.
Yes, very accurate. And this close agreement between the predicted and experimental values really validates their approach and demonstrates the power of using statistical modeling to optimize biochar production.
The study concludes by highlighting the various environmental and economic benefits of producing biochar from these agricultural residues using vacuum pyrolysis. They mention carbon sequestration, soil fertility enhancement, sustainable waste management, and promoting a more circular economy.
Absolutely. This study provides a compelling case for using vacuum pyrolysis to transform agricultural waste into a valuable resource that can address multiple environmental challenges.
And it also reiterates the many potential applications of this optimized biochar, from improving soil health and crop yields to cleaning up pollutants and mitigating climate change.
It's a really exciting area of research with a lot of potential to contribute to a more sustainable future.
So after taking a deep dive into these two sources, it's clear that biochar and hydrochar are fascinating materials with distinct properties and a wide range of potential applications. And the advancements in optimizing biochar production from agricultural residues like sugarcane, bagasse, and corn cob using techniques like vacuum pyrolysis are opening up new possibilities for sustainable waste management and environmental remediation.
It's amazing to see how much research is being done to unlock the full potential of these materials. From characterizing their microscopic structures to understanding their complex chemical behaviors, scientists are really digging deep to figure out how to best utilize biochar and hydrochar to address some of the most pressing challenges facing our planet.
It's clear that these materials are much more than just waste products. They're increasingly being seen as engineered materials with the potential to revolutionize how we manage resources, protect our environment, and build a more sustainable future. And it makes you wonder, what other innovative applications for biochar and hydrochar will emerge in the years to come? How will these materials shape the future of agriculture, environmental remediation, and even energy production? It's an exciting time to be following this field, and we can't wait to see what new discoveries and breakthroughs lie ahead.
I think it's also a good reminder that sometimes the solutions to our biggest problems can be found in the most unexpected places. Like, who would have thought that agricultural waste could hold the key to combating climate change and improving soil health? It's a testament to human ingenuity and our ability to find innovative solutions when we put our minds to it.
Well said. I think that's a great note to end on. Thanks for joining us for another deep dive into the world of biochar.